Hello everyone, this is Dr. Andrew Chrysler teaching EE 4418 at Idaho State University. In this series of videos, I'll be talking about the Fourier Transform, which is chapter 3.1 in the Modern Digital and Analog Communication Systems. If you'd like to follow along, you can find this information in page 93 to 99 of the 5th edition. So first, let's talk about the Fourier Transform. So electrical engineers must think about signals in terms of their frequency spectra, and we must also think about systems in terms of their frequency response. We can use the Fourier transform to move back and forth between time domain signals and their frequency spectra. You probably learned this in your signals and systems class, but we're going to review it here because it's important for communication systems. So the definition of the Fourier transform is given by this integral, and sometimes we also write it using the notation where we have f in a script being taken of a time domain signal. And we also have this definition of the inverse Fourier transform, where we get a time domain signal by taking an integral of a frequency domain spectra. And again, we also sometimes denote this using a scripted f with an inverse of the frequency domain spectra. So let's refresh ourselves on why this works and how they're related. So first, let's think about an aperiodic signal, GT. And this aperiodic signal, GT, is something that's not repeating. If we're going to work towards finding the Fourier transform and the inverse Fourier transform of GT. So let's think about GT as if it was this signal where there's just one signal and it's not repeating. And now let's turn it into a repeating signal, and we'll call this repeating signal G sub T naught. And this T naught denotes the period with which the signal GT repeats. So the signal is going to repeat every T naught seconds, and that's the period. So if we were to transform that non-repeating signal into a repeating signal, it might look like this, where every T naught, the signal is going to repeat. So if the repeating signal, GT naught, if we have that, we can represent this repeating signal using an exponential Fourier series. Again, you probably saw this in your signals class. If we were to do that, we would write the time domain signal, GT, as an infinite summation of some coefficient dn multiplied by exponentials. Each coefficient dn would be found by taking this integral over a period of the signal, GT, and each different dn would be based on different numbers, where n could be 0, plus or minus 1, plus or minus 2, etc. There's another review of this in chapter 2.9 of this textbook, or you can look this up in your signals textbook. So if we were to make the non-repeating signal, GT, into a repeating signal, it would look like this, and we know what the coefficient would look like and how to represent it as an infinite summation. So what would happen if we kept increasing T naught? What if we kept increasing the distance between each peak that occurred in our repeating signal? Well, if we did that, it would continue to space out, and we can see that eventually, if that period approached infinity, then our repeating signal, G sub T naught, would actually be equal to our signal, GT, the original signal that we were interested in. So in that limit, we could make the repeating signal equal to our signal. And we can say this mathematically by writing this limit. So now we know that if the period approaches infinity, so that each one of those peaks gets further and further apart, then our repeating signal would be equal to the original signal we started with. Therefore, this will also hold true for the exponential Fourier series representation. So even if we write our signal using an exponential Fourier series, we would still have this same limit, which would hold true. So this would be the exponential Fourier series representation, and this would be the coefficients. And if we were to keep spreading out the periodic signal so that the period gets larger and larger, eventually we would see that the signal gt naught would be equal to gt, and we could change the limits on this integral from t naught half to infinity and minus infinity. And that's because as we make the period larger and larger, eventually we would just reach the case where we have gt as our actual signal. Now we know that if the period approaches infinity, that we will have the periodic signal being equal to the original signal. We'll continue this in the next video.